Alrighty, good morning, gang. Let me go ahead and close my office door here and then we can get started. All right. We don't need that. We don't need this or this. Or that. But we do need these. And this is not connected. Oh goodness, connected. All right. So today we're going to talk more about derivatives, of course, differentiation rules. Specifically, the chain rule. Don't worry about this. There's other stuff. So we kind of introduced the chain rule a little bit the other day. I'll take a much closer look today. One of you is working pretty well. One of you is working like crap. I suspect you're the crap. Forgive me, I think my whole body's just running a little bit slow. I didn't have the heat on last night. Woke up and it's like 60 degrees inside, so I'm just a little bit creaky today. But here we go. It says, today is the chain rule. Okay. And the section, I think this is like 3.5, 3.4, sorry. And we talked about this a little bit on Monday. The idea is that there's an inner function and an outer function. And what we want to do is learn how to differentiate those composites. So in order to kind of warm you up for this, I'm going to go back over a little bit what we did. What we want to do, question. Is there a formula for the derivative of composite functions? And I don't remember the exact examples we used, but like sine of e to the x, or maybe the square root of the natural log of x, or, you know, you can imagine all sorts of things like this. Well, the sort of fun, you know, we can take we don't know how to do inverse tangent yet, so I should stay away from that. But how about like, what other sort of fun composite functions? We could take secant of x and then raise that whole thing to like the 3/2 power, right? Stuff like this. You know, I could shove a polynomial inside of tangent. What makes all of these composite functions is that there's an inner function and an outer function. And one of the things you need to get good at for the chain rule is just identifying the inner and identifying the outer. There's a notation thing here that's going to take a little getting used to. I'm going to call the inner function u, and the outer function f of u. Don't get carried away with the middle school humor there, fu, but let's try it like this, because some of the problems in your homework set ask you to identify these and even write them as ordered pairs, which is a little bit awkward. So I just want to see how comfy you are. So if I look at this guy, the sine function, right? Sine of e to the x. My inner function there is what?
E to the x.
Yeah, exactly. That's e to the x, right? That's the thing that's been shoved inside the sine function to create this guy. And what's my outer function there? If I think of the e to the x as u, then what's my outer function as a function of u?
Sine.
Good, sine of u, we would say, right? Remember, a trig function doesn't have any meaning unless you give it an inside. And the idea here is that I want these two things when composed to form this thing. So sine of u, and u is e to the x. So this is really sine of e to the x. That's the vibe. So let's try these others. Where do I want to put this? Let's put this guy. We'll just do a few more of these. So here my inner and my outer. My inner function, which I'll call u here, would be what?
X.
Let's see. So this is one of the funny things is that, yeah, you can kind of like keep diving in layer after layer. And if you penetrate all the way in here, X is the innermost layer. That's true here too, right? We could have considered this kind of 3 layers, right? Sine and then e to the and then X. But I'm thinking of this as the inner and the square root as being the outer. So if the variable you're labeling as your inner is just the variable, then we need to come out 1 layer more. So I would say the inner here is ln of x, and the outer here, the square root function. So f of u would be square root u. Although you're not wrong to say that the all the way inner thing here is x. It definitely is. But we want to come out just one layer out so that I can think of this as just 2 functions rather than as 3 functions layered together. All right, let's try 1 more. Let's try 2 more. I'll do secant over here, and then I'll pull the tangent example down there. So again, I'm going to call the inner u, and I'll call the outer f of u. What do we think is our inner function here, and what do we think is our outer function here?
Secant x is the inner.
Good, yeah, secant x is the inner.
And then u to the 3/2.
Excellent. All right, and then this last guy. The inner function here, u, for this weird tangent thing, what would that be?
X squared plus 3x minus 2.
Good. And the outer function?
Would be tan u.
Yeah, this one's just tangent u. And that's the game. So, question is there a way to find the derivative of things like these? And the answer is yes. You first need to think of it as a clear inner and outer. And then we have the following theorem, which is the chain rule. It says if you want to differentiate I should say if we'll put the conditions down here. If u equals u of x is differentiable, and f of u is differentiable, then the derivative taken with respect to x of f of u of x, so like f is your outer, u is your inner, and x is the variable. This is going to be equal to f primed of u times u primed of x, which you could also think of as f primed of u of x times u primed of x. This would be the bottom way would be the way I'd write it. The book writes it the top way. The idea is you differentiate the outer, leaving the inner alone inside. So you kind of just differentiate the outer layer and leave the inside alone, but then you multiply by the derivative of the inner layer. It's a sneaky thing. And I didn't want all the stuff that comes before the formula to be too long, but really we should say if this is differentiable at A and this is differentiable at U of A, then this thing exists at A. But, you know, just think of it as a differentiation formula and everything will come out much more cleanly. All right, so this is the big deal. It can be written in Leibniz notation, and in Leibniz notation, it has some sort of, I don't want to say intuitive understanding, but there's a way of writing this so that the notation is nice and evocative of what is true. I want to use the same symbols that your book uses, so let me, back here real quick. Forget what they use for the, yeah, dy, dv, yeah, sorry. So they say here, if y is f of u and u equals g of x, then dy dx is equal to dy du times du dx. And this says the exact same thing. Some people like this way of writing things more because you can kind of pretend like you're canceling the fractions, right? Like you're canceling the du's. That's not what's going on here. I want to be really clear about that. We are not canceling the du's. The du's are differentials. They're geometric objects that can't be canceled. They're not real numbers. They don't have meaning like that on their own. Let me see. After the word in, oh, Leibniz, L-E-I-B-N-I-Z, Leibniz. This is Wilhelm Gottfried Leibniz. Remember the two notations we have for derivative are like the prime notation and the Leibniz notation, which is the dy dx notation. So these say the same thing, right? This would be dy du. This, if you prefer to write it like this, dy du, and this would be du dx. So they're saying that the derivative of the whole composite function is the derivative of the outer with respect to the inner times the derivative of the inner with respect to the innermost variable. That's the same thing here, right? This says that the derivative of the overall function, which is f of u of x, is equal to the derivative of the outer with respect to the inner function, with respect to the variable u, multiplied by the derivative of the inner function with respect to the variable x. Same statement. Yes, of course. Yeah. So let's take the derivative of all these functions that we just identified the inner and outer of. Just want to make sure everybody's comfy with what these say. So I'll hold here for about another 5 seconds, and then we're gonna take some derivatives. Yeah, so Fabrice, if you go back to the video where I introduced the Leibniz notation, there is a meaningful difference. dy dx is a noun. d dx is like a machine. dy dx is y prime. dy dx is the derivative of y taken with respect to x. d over dx is a machine that differentiates whatever you put in front of it. So d dx, this is a differentiation machine. This is f prime of x, the derivative. That's the way to think of it. Remind me at the end, and I can, like after class, and I can link you to the part of the video where we talked about that. It's a weird thing. It takes a little getting used to. All right. So let's come back. Let's come back to each of these functions that we were playing with before. I want to differentiate example. I want to find the derivative of f of x equals sine of e to the x. So we identified the outer and the inner. The inner function here is u equals e to the x, and the outer function here, we said I can think of this as f of u, where f of u is sine of u. And then if you string those together, we should be able to get our derivative. Now, according to the chain rule, the derivative of this apparatus should be the derivative of the outer with the inner left alone times the derivative of the inner. So let's come back here. So, and compute f primed of u and u primed of x. All right, f primed of u, if I differentiate this function with respect to u, what do I get? What is the derivative of sine u?
Cosine u.
Good, yeah, it's cos u. And if u is e to the x, what is u primed of x?
E to the
E
x.
to the x.
E to the x, all right. So now, according to the chain rule, the derivative of my function here, f primed of x, should be equal to f primed of u times u primed of x, right? This is going to be cos of u times e to the x. But this doesn't look how it should, right? I've got two different variables in here. So we should plug in for u here. What is u? U is e to the x. So this is cosine of e to the x times e to the x. Is this making sense?
Yes, sir.
It's a little bit weird.
If it If it wasn't like e to the x and it was like a constant or something, or I don't know, something that wouldn't equal 1 or 0, would you put the original u or would you put the prime of u?
The thing that goes inside here is always the original u. The thing that goes
Okay.
outside here is always the derivative.
Okay.
Let me show you how I would do this. So this is like being very careful. All this, right? But the normal way to proceed here, if I wanted to differentiate sine of e to the x, I would say, all right, I'm going to differentiate the outside and leave the inside alone, then multiply by the derivative of the inside. So that's cos of e to the x, differentiate the outside, leave the inside alone, times e to the x primed. And then I would say, okay, well, that's cos of e to the x times e to the x. This is the kind of normal way we do this. But I want to go through a few more of these being very careful so that you can see that it really does the same thing as this sort of normal procedure. Because if you just jump to this normal procedure, people usually have a hard time understanding where all the pieces are coming from.
Would you ever have to multiply it out at the end?
Yeah, oh yeah, oftentimes we will have to do a lot of algebra at the end. Now here, there's nothing we can multiply out. This e to the x is stuck inside of cosine. This e to the x is outside the cosine, and there's really no way we can combine those, right? Like there's no rule that lets me bring a multiple outside a trig function inside, especially a variable. But yes, often we'll have algebra to do after the fact.
Okay, thank you.
Let's try the square root of the natural log. So let's find the derivative of f of x equals square root ln x. Oh wait, we don't know how to differentiate ln x yet. Hang on. Yeah. All right. We're gonna have to skip over this one for now. Sorry. Let's do this one. F of x equals secant x to the 3/2. I'll show you how to differentiate the natural log soon. We're just not quite there yet. Okay. Any ideas what I should do here?
Can you break it apart?
Yeah, we identify my inner and my outer, kind of break it into an inner and outer part. So the inner part here is u equals secant x, and the outer, we said f of u here is u to the 3/2 power. So f of x really is f of u of x. And that means that my derivative, f primed of x, should be f primed of u times u primed of x, right? So I need to calculate u primed. What's the derivative of secant x? This one should be fairly
Secant x tan x.
Very good. Yeah, secant x tangent x. And these trig derivatives, we got to learn these cold. They got to be fast. That's beautiful. And the derivative of my outer, f primed of u, what is that? If I differentiate u to the 3/2.
It's going to be 3/2 u raised to 1/3.
Almost. So we need to subtract 1 from 3/2, right? So it's
Right.
3/2 minus 1/2, which is 2 halves, or just 1. Wait, sorry, what did I do here? 3 halves minus, sorry. We are subtracting 1 from 3 halves, which is 3 halves minus, I said 2 halves, but I did 3 halves minus 2 halves, which is 1 half. All right. So f primed of u is 3 halves u to the 1 half, and u primed of x is secant x tangent x. And then we have to plug back in for this u. What was this u? It was secant x. So this is 3 halves times secant x to the 1 half times secant x tangent x. And you can see what happened here, right? I differentiate the 3 halves power, leaving the inside alone. And then I multiply by the derivative of the inside. So again, if I was doing this quickly, I would say d dx of secant x to the 3 halves. My outer function is the power, the 3 halves power. So I'm going to differentiate that, leaving the inside alone. There's the derivative of the outer function, right? Differentiating the 3 halves power, I bring the power down, subtract 1 from the power, and then I multiply by the derivative of the inside. And I would write it out like this first, and then go ahead and compute the inner derivative. And we get the exact same thing, just done much more quickly. All right. Let's see if we can't do that. Didn't we have one more? Yeah, let's see if we can't do this last one, this tangent, without the explicit breakdown there. So this was x squared plus 3x minus 2 inside tangent. So what I want to do here is acknowledge that this is a composite function. Oh, I'm sorry. There we are. There's that one. What do you guys want? And probably this one is the one you guys wanted, right? Yeah. So the long way is up top, the short way is downstairs, down at the bottom.
How can we practice learning the derivatives of the trig functions?
Solve lots of problems that involve derivatives of trig functions. So you notice that the homework, right? Going through the homework is really good. Here, give me 1 second. Let me make sure people are done writing here. If Madi and Fabrice could let me know when they're done, or if you guys could just give me a quick thumbs up or something when you're done writing so I can show in the book something.
I have a quick question on this problem.
Sure.
Why didn't you get rid of secant x, like when you found the derivative at the bottom? Like, why didn't you just put tan x?
Well, because the derivative of secant is secant tangent.
Oh, okay, okay.
Yeah. So the derivative of secant x is secant x tangent x. Yeah, so that's
Okay, thanks.
No worries. Yep. I could, if I wanted to, if I was being clever, I could combine these two. This is secant to the 1 half. This is secant to the 1. So I could put these guys back together as secant to the 3 halves if I wanted, but I think that would be confusing. So this is the derivative of the outer with the inner left alone, just differentiating the 3 halves power. And then this is the derivative of the inner, which is just the derivative of secant. All right, real quick, how can we practice more trig derivatives? Well, we come in here to our handy dandy textbook, section 3.3. And you'll find lots and lots and lots of problems. So I assigned you guys a fair chunk of problems, but there's many more that I didn't assign, right? Because I can't, if I assigned every problem in the book, you guys would hunt me down wherever I live and key my car and poop on my porch and stuff. So I don't want to torture you that way, and I don't want to clean poop off my porch. But if you want more practice problems, the book is really the way to go. There's so many good problems in here. So I would strongly recommend, if you really want to understand this stuff in a deep way, that you solve every single problem in the book. For as long as I've been teaching math and for as long as I've been a student of mathematics myself, that's been the approach that's been taken by people who really want to get good at this stuff. Just solve all the problems. And you see, these aren't just straight trig derivatives, but they're all derivatives that involve trig functions. So you have to remember the derivative of sine as one step of problem 1, or you have to remember the derivative of cotangent as one step in problem 16. And that's the way to really reinforce these things. Instead of just doing that one thing over and over again, do a bunch of very similar things that all rely on those things you're trying to remember. It's like, you know, how do you learn to hammer a nail? You don't sit there and hammer one nail over and over again, you go build a fence, right? And then you're calling on that skill again and again and again, and eventually that skill will become second nature. All right. If you don't have a copy of the textbook that you like, if you don't have access to a copy of the book that you find easy to flip through and look at and grab problems out of, send me an email and I can help with that. All right. So we want to take the derivative, focus. You want to take the derivative of the tangent of this quadratic. And I aim to do this without breaking things down really explicitly. So tangent is my outer function, and x squared plus 3x minus 2 is my inner function. To get started on this, I just have to remember what the derivative of the outer function is. So what is the derivative of tangent?
Secant squared.
Good. So I'm going to differentiate the outer function, the tangent, to a secant squared and leave the inside alone. And then I'm going to multiply this whole thing by the derivative of the inside. And I'll just write that out schematically. That's how it's done. And now in my next line, I'll compute this derivative. So this is going to be secant squared of x squared plus 3x minus 2 times 2x plus 3. And that's it. So you can combine this rule with the quotient rule, with the product rule, with all of our trig derivatives, and these can get pretty gnarly. You now have the tools you need to learn how to differentiate pretty much any function. We haven't yet talked about inverse trig functions, logarithms, or hyperbolic functions. We won't be talking about hyperbolic functions in this class, but we are able to discover some cool stuff using this. So we mentioned that we don't know how to differentiate the natural log yet, right? Let me see if I can convince you what the derivative of the natural log is. And this will kind of serve as a gentle introduction to implicit differentiation. So can we use the chain rule to find the derivative of y equals ln x. Why this camera's like, this paper is supposed to be blue, it's showing up some sort of weird green. All right. There's a challenge here, of course, that's that, you know, right out of the gate, I have no idea what the derivative of ln x is, but we can rewrite this as e to the y equals x, right? This and this mean the same thing. This is the definition of the natural log. This is, by definition, of the natural log. And now we can differentiate. If I apply the operator ddx to both sides here, right? So from here, I take derivatives on both sides. The right-hand side, the derivative of x is 1. The left-hand side requires the chain rule. My outer function is e to some stuff, and my inner function is y. So I differentiate the outer, leaving the inner alone, and then I multiply by the derivative of the inner, which would just be y primed, right? Think same way we did up here. Differentiate the outer, leave the inner alone. That's the e to the y, and then multiply by the prime of the inside, y primed.
Where did you get the inside though?
So the inside here is y. So kind of think of this as u, right? If this was a u, then I would have e to the u times u prime from my chain rule. It's just a different label. Instead of using u for my inner function, I'm using y for my inner function. Kind of what's going on here is we know y is the natural log of x. This really is a function. It's not just a variable. Y is ln of x. So e to the y is e to the ln x. It's a composite function. And my goal is to find y prime. So what we end up with here is an equation that I can solve for y prime. So this is by the chain rule. Everything on the left here is the chain rule, right? I differentiated the outer, leaving the inner alone, just like the derivative of e to the x is e to the x. The derivative of e to the y is e to the y. If this was e to the x, then I would have e to the x times x primed. And x primed is just 1. But y primed is the thing I wanted. I wanted the derivative of y equals ln x. I wanted y primed. So all I have to do now, this is by the chain rule, now all I have to do is solve for y primed. This implies that y primed is 1 over e to the y. But e to the y is x. So y primed is 1 over x. In other words, the derivative of ln x is 1 over x. And this is just one of the many, many, many very cool things we can do with the chain rule. We'll get a lot more practice with this sort of thing when we talk about implicit differentiation. But I'm not going to go there just yet. So instead of digging deeper into that direction, I just wanted to show you this because it did come up. So if y equals ln x, then y primed is equal to 1 over x, i.e. the derivative of ln x is 1 over x. All right. So this is a fun example. It's a little bit challenging. Let's get some more kind of foundational practice with the chain rule. If this feels like magic for you right now, don't panic. Just take the time and reread it. I'll be running through a lot more arguments like this after exam 1, but for now, this is just one cool thing we can do with the chain rule that solves a problem we hadn't solved yet, finding the derivative of ln x. So let's grab some extra chain rule practice. Oh yeah, we can do arbitrary other exponentials now too. So we've seen before we know that the derivative d dx of e to the x is e to the x. But what about other exponential functions like 2 to the x or 5 to the x or 1/3 to the x? What about more general? Like these guys. So if e to the x is its own derivative, how can we figure out the derivative of 2 to the x or 1/3 to the x? Turns out there's a sneaky way to do this involving the chain rule and the natural log. So we have to get a little bit clever. There's an algebra trick here. A to the b is the same as e raised to the natural log of a to the b, right? Because e raised to the natural log of anything is just that thing. But now you can use your rules for logarithms to say, well, this is really e to the b times the ln of a, right? A log of a power. That power can come down as a multiple. This is kind of an odd trick, but it's useful. It's useful here, and it's useful in some other surprising places too. So, using our algebra trick, we can write f of x, which was 2 to the x, as e to the x times the natural log of 2. No calculus here, just algebra. These things happen to be equal, like actually equal to each other. Because a to the b is always e to the b log a, 2 to the x. You know, kind of think of x as being b here and a as being 2 here. So if I want to calculate the derivative, f prime of x, this is going to be d dx of e to the x times the natural log of 2. Yeah, it's funny. So you really got to take a second to think about each of these two equals here in this algebra trick. This step is a big deal, and this step is a big deal, and neither one of them is obvious. Think back to your, college algebra, pre-calculus class when you learned about exponentials and logs. E raised to the power of the natural log of some shit is always just that shit, right? Because
Yes.
e's and natural logs undo each other. That's the first equal sign. So some shit is the same as e raised to the ln of that shit. And then from here to here, I'm using the rule that says, I can tuck it in here somewhere, that the ln of a power is the same as the power times the ln of that number, right? Powers can come down. And I'm doing that within the power here, right? I'm doing all of that up here. So just this piece is equal to this piece. And all of that is happening kind of inside of the E. So the
Okay, I got it now. I understand it now.
Cool. It's very sneaky. If this takes a second to click, don't feel bad. It's very sneaky. If it doesn't click today, don't feel bad. But make sure you get it down and make sure you think about it, because I promise you it's true and it is surprisingly useful. For example, here, what I'm now doing with this is differentiating a composite function. Here's my inner, right? X times the natural log of 2 is my inner, and my outer is the exponential. So here, I'll say it, my inner is u equals x times ln2. It's worth noting that ln2 is a constant, right? It's just a number. It's like 0.6. And my outer is e to the u. So when I differentiate this, I'm going to differentiate the outer, leaving the inner alone. And then I'm going to multiply by the derivative of the inner. The derivative of the outer, the derivative of e to the u is e to the u. What's the derivative of x times the natural log of 2? This might look like it's complicated, but it's not. It's like x times 5 or x times 1/2. ln2 is just a constant. This is a constant multiple. So you just differentiate the x, right? The derivative of x is 1. So out of this, we get e to the x times the natural log of 2 times 1 times the natural log of 2, or just natural log of 2. And then you can undo your algebra trick. E to the x ln 2 is 2 to the x. So this is 2 to the x times the natural log of 2. And that's the derivative of 2 to the x, i.e. the derivative of 2 to the x is 2 to the x times the natural log of 2. And this works in general. You can swap that 2 for any other positive base, and this works great. So I would say, similarly, the derivative of, what was the other one we had? 1/3 to the x. If you want to differentiate the base 1/3 exponential function, you'll just get 1/3 to the x times the natural log of 1/3. And you can check that this works with e to the x too. If you want to differentiate e to the x, you would get e to the x times the natural log of e. It's just that the natural log of e is 1. So in full generality, the derivative of b to the x, the base b exponential for any positive number b is b to the x times the natural log of b. And this is a rule you should remember. If you don't remember how it's cooked up, you know, if this doesn't stick, that's not the end of the world in Calc 1, but this down here does need to stick. And in my experience, the best way to get this to stick is to really understand it. So I would encourage you to go back through this, see if, spend some time on a whiteboard at the library, try to convince your friend, try to convince somebody else that this is true, and you will, along the way, convince yourself. What other fun examples do we have that we can do now that we couldn't do before? Certainly there's some pretty wild looking exponentials out there, exponential composites. You can look at one or two of those. We should look at something involving product and quotient rules. Let me have a peek at your textbook. Yeah, I guess we should look at some multi-layered things. Some quotient rule things. Okay. Does anybody need more time on this page? Sorry, my phone's blowing up. Okay. All right, yeah, let's try a few more problems. So I run the math team here at Santa Fe, the academic math team, and one of the competitions that we enter in every year is called the AMATIC SML. And these guys are very cheeky, much like the Putnam competition, if you've heard of that. They like to insert the year into a problem, right, the current year. So let's find the derivative of f of x equals 2x squared plus 1, all raised to the power of 2021. There's a bunch of ways to do this. Some of them suck. Some of them suck a little bit. Some of them are reasonable. Option 1, the suckiest. Multiply 2x squared plus 1 by itself 2021 times. In other words, FOIL it out. FOIL it out 2021 times, meaning you multiply this thing by itself, you FOIL it once, and then you distribute another copy of this over that, and then you distribute another copy of this over that result, and then you take what you get from that and you distribute another copy of this over that, and you keep going until you've done that 2021 times. And you don't make any mistakes. And then you use the power rule. So option 1, option the shittiest. Multiply out, then use the power rule. Multiplying this out will take the rest of my natural life. I don't really want to do that. I don't think you do either. Option slightly less shitty. Use the product rule. $2,021 times. It's not a lot less shitty, but it's a bit less shitty. Option not shitty. Use the chain rule. Right? Instead of multiplying this thing all the way out and using the power rule, or instead of thinking of it as this thing times itself a bunch of times and using a shitload of product rules, I can think of this as the inner and the power here as the outer. So my inner is u equals 2x squared plus 1. My outer is f of u equals u to the 2021. So if I want to differentiate this function, I can differentiate the outer, leaving the inner alone. That means I'll bring that power down. I'll leave the inside alone. And I'll reduce the power by 1. And then I multiply by the derivative of the inside, which I'll write schematically as this. So what do I get? I get 2021 times 2x squared plus 1 to the 2020 times the derivative here, which is 4x. That's it. Now we can clean this up, and we should clean this up a little bit. 4 times 2021, I somehow don't trust my arithmetic. I think that's going to be something like 8,084. So that's 84x times 2x squared plus 1 to the 2020. That's the derivative. And it's the same thing you would get if you used either of these shittier options and then spent a long time calculating and a long time simplifying. Comes out right away with the chain rule. And I even wrote a bunch of extra shit here, right? Like we didn't really need to write this. We could have figured this out. Just differentiate the outer, leaving the inner alone, multiply by the derivative of the inner. Questions on this example? It's gonna take some time. It's gonna take some practice, but really just solving more and more and more problems is the way to get comfy with it. Is there an individual step here that feels strange that we can talk about a little more?
I'm kind of confused on the first derivative of f of u. Oh, never mind. I get it.
So yeah, what I used to do is, this doesn't work quite as well, but cover up the inside, right? If I cover this up, it's just some shit to the 2021. And if I want to differentiate the outer function, I just totally ignore what's inside. I brought down the power, 2021, and I reduced the power by 1. So this is the derivative of the outer, leaving the inner alone, right? I just brought, here's my old power down here, and this is n times x or whatever to the n minus 1. That's the derivative of my outer, leaving the inner alone, right? 2021 times u to the 2020. And then I say, okay, well, I need to multiply by the derivative of my inner. That's what the chain rule does. So kind of derivative of the outer, leaving the inner alone. Here's the inner left alone. And then I go, oh, okay, well, I need to also multiply by the derivative of the inner function. That's what the chain rule says. So do we all see this part? You see the old power down here and the power with 1 taken away up here? It's just like the derivative of x to the 2021. It would be 2021 x to the 2020. The part that's not covered up right now is f primed of u. But now when I plug in for u, what is u? It's this. Okay. And then I also need to multiply by the derivative of u. Okay, well, that's this. And then in my next line, I just went ahead and calculated this derivative. Everything else stayed the same. This is all the same. But if you differentiate 2x squared plus 1, the derivative of 2x squared is 4x. And the derivative of the plus 1 there is 0. So this piece is this. And then here to here, I just multiplied the 4x and the 2021. I hope I did that correctly. I think I did.
Thank you.
Of course, of course. Yeah, this shit feels like magic at first. It's weird. It is. If it doesn't, there should be this transition moment, right? Where it goes from like feeling really weird and like magic and not making sense to being the clearest thing in the world. And that'll be like a click, like a light bulb moment. And it will come. Chain rule is on the test. Yep, chain rule is the last thing on the test.
So this is kind of a dumb question, but when we see a problem, how do we know when to use the chain rule? Like when we look at it, what makes us know, okay, use the chain rule for this?
It's a good question. That's kind of what I was trying to suss out here, right? It's like, yeah, okay, so we recognize that we have other ways we could attack this. I could, like in the past, when you've been given something like this, the power was never anywhere near this big, right? Like, but if this was just a 2 or a 3, then you would multiply all this out and use the power rule. The trick to recognizing when you should use the chain rule is when there is a clear inner and outer function. All right, that's really the trick. Most of the things that we use the chain rule on can only be done with the chain rule. This isn't a good example in that sense, right? Because this could be done 2 other ways. But for the most part, chain rule problems can only be done with the chain rule. So let's look at 1 or 2 more examples. I think as we work more examples, as long as you really think along with me, the answers to these questions will become kind of self-evident.
Okay, thank you. And then on the test, will you, for the problems, will you ask, or will it be like solve with the chain rule or the quotient rule, or will it just be like find the derivative?
Much more the second thing. Yeah, much more like just calculate the derivative, or maybe not even that. It might just say find the equation of the tangent line. So it's up to you to figure out that you need a derivative and then to figure out which differentiation rule to apply. There might be some problems where I give you a hint or a little nudge, like hint use the chain rule or hint use the quotient rule. But for the most part, you're going to be on your own when it comes to figuring out which method to apply or which tool to apply.
Okay, thank you.
All right, I want to try one slightly gentler example, and then we're going to go to a slightly harder example. Let's find d dx of, what was this? There's one in here that I liked. No, yeah, okay. let's do e raised to the power of, I already wrote sine x. All right, let's do this. So I want to find the derivative of e to the sine x. So again, I have an inner. My inner is sine x. My outer is e to the u. All right, if u is the inner sine x, then the outer is just e to some stuff. So the way I differentiate this is by differentiating the outer, leaving the inner alone. If I differentiate e to some stuff, I just get e to that stuff. This would be e to the sine x, right? Differentiate the outer, leave the inner alone. And then I multiply by the derivative of the inside. And the derivative of sine is cosine. So this is e to the sine x times cos x. Yeah, test is going to be on the 10th.
So I'm confused on finding the inner and outer with the exponents, because I would think that like the sine x would be the outer.
Well, I'm thinking of this as an exponential function. So because the variable is kind of in the power, right? We think of this as an exponential function. If this was some variable base raised to a constant power, then you'd be right. The power would be the outer. But think this is like e to the x, but instead of just having an x inside, it's sine x. So it's sine x plugged into e to the x. Right? If you take e to the u, which is that exponential function, and you plug in for u sine of x, then you will get our guy here. So the inner here really is sine x, the outer is the exponential. I understand how that can be a little bit confusing, but if the power is constant, then the power is the outer. If the power is variable, then you need to think of the function as being exponential, which means probably whatever's going on with the power there is going to be the inner, and the outer will be the exponential.
Okay, and then like when you look at e to the sine x is very similar to e to the x with the derivative where it just doesn't really affect it.
Yeah, so here's a nice kind of general rule. The derivative of e to some shit is always e to that shit times the derivative of that shit. Kind of a generalized exponential rule. This will always work out this way because your outer here is always the exponential and the shit is the inner. So this really is just the chain rule. Assuming that your shit here is a function of x, right? Assuming that there are some x's in the shit. That sounds, I feel like we could get a good joke there if we tried. Anyway, other questions on this? Okay, I do want to look at something a little bit more challenging. I want to compose multiple functions. I'll take an example from your book so you can look in here. Let's look at e to the secant of 3. That's somehow more complicated than we need. Here, let's do it. All right, and this will be the last thing I'll do with, as an example today. This is very similar to the last problem, right? The last one was e to the sine x. This is now e to the sine of x cubed. So I've got several layers. I've got like an outer, an inner, and then an even more inner. So if I follow the recipe here, this should be e to the sine of x cubed times the derivative of sine of x cubed. The challenge here is that this is no longer a straightforward derivative. This also requires the chain rule. So this is e raised to the power of sine x cubed. And now here I need a chain rule. What is the derivative of sine of x cubed? Well, I differentiate the outer, leaving the inner alone. The derivative of sine is cosine. So this is cos of, leave the inside alone, x cubed. And then I need to multiply by the derivative of his inside. So it's a chain rule within a chain rule. Now finally, the derivative of x cubed is 3x squared. So this is e raised to the power of sine of x cubed times the cosine of x cubed times 3x squared. I'd be happy to kind of review the Leibniz notation at the end here. Yeah, I'm fine with that. Don't stress. But I want us to focus on this example for right now, because this sort of thing, this happens more often than you would think, piling chain rules together. Yeah, you notice most of the day today I've been using the variable x, right? Just x's and y's. But you could use the variable theta in place of the variable x. I'm just trying to keep things maximally simple because I know the chain rule is hard to digest at first. When we talk on Friday, I will do more examples. And then when we review for our test, we'll do more examples. And I will slowly introduce the use of other variables over time. I just kind of want to be gentle at first here. But certainly you could use the symbol theta everywhere here, as long as this is dd theta, and then everything would go the same. You can swap all the x's for thetas and nothing changes.
I had a quick question about something.
Sure, Robert.
So the rule is that f of u, you take the derivative times u derivative, correct?
Yeah, differentiate f, leaving the inside alone, and then multiply by the derivative of the inside, multiply by the derivative of u.
That's why you're leaving e to sine x cubed, because e is to the derivative is just e. Okay.
Yeah, so the derivative of e to some stuff is always e to some stuff, right? But then you have to multiply by the derivative of the stuff.
Got it.
I'm kind of using this rule in my first line here.
Because every time I've seen it, it's the same thing in the first part and then something different in the second. So I was just want to double check that.
Yep, that is how derivatives of exponentials will always work. This is why mathematicians love exponential functions so much, because no matter how complicated the shit is, the derivative of e to some shit always starts with e to that shit.
Yeah.
It's always proportional to itself. But then it can get more complicated depending on how complicated the shit is.
Now in the test, are you going to have us using e there, or is it going to be some kind of exponent?
I could ask you to differentiate 1/2 to the sine x or 2 to the x cubed. Things like that would be fair game.
Okay.
Because we did discover how to differentiate other base exponentials. So if we want to do a quick one like that, I can. So like, let's combine all this stuff. So we want to talk about other variables. So I'll say h of theta is 2 raised to the power of secant theta. And let's find h primed of theta. Practice with the notation. H primed of theta is the derivative of my function taken with respect to theta. So that would be d theta of 2 raised to the secant theta. So here my inner is secant theta, and my outer is 2 to the u, or I should say u equals secant theta. So then 2 to the u is 2 to the secant theta. So to differentiate this, I'm going to differentiate the outer function. The derivative of 2 to the u is 2 to the u times the natural log of 2, right? Remember, the derivative of any other base exponential is like this. So I would have 2 to the secant theta times the natural log of 2. That's differentiating the outer, leaving the inner alone. And then I would multiply by the derivative of secant theta. And the derivative of secant theta is secant theta tangent theta. Something like this is about the right speed for an exam question. If the question is just like straight calculate the derivative, don't do anything else, this is about the level of difficulty I would expect to see on a test. Now, is this exact problem going to be on there? Probably not. A base 2 exponential is kind of like, it's not something that shows up a whole lot, but you know, we should be comfy with this. We shouldn't be terribly intimidated by this by the time we get to the test. If it looks intimidating right now, that's okay. We just learned the chain rule. Of course it looks intimidating. But don't be too frightened by this. After you come through the homework and solve all those chain rule problems, you'll look back at this and go, oh yeah, this makes good sense. Okay, I have just a few seconds left to talk about notation, so I'm going to do that. I want to remind everybody, because it's easy to forget, that ddx, this is like a machine. This is a differential operator. This says, I should say, this thing says differentiate whatever is to the right, treating x as the variable. Right? If I had like dz of some stuff, this would say differentiate whatever is to the right treating z as the variable. So the way I read this is, take the derivative of this stuff with respect to this variable. And the other sort of notation we've seen here is stuff like dy dx. So these things are commands. Or operators, they're called. I like to call them verbs. They tell you to do something. They're kind of verbs. They tell you to do something. Dy dx, this is what you get when you apply the operator ddx to y. This is also just called y primed, or if y is f of x, f primed of x. This is the derivative. is the derivative of y, or f of x, if so labeled, taken with respect to the variable x. So d over dx, or d over d whatever, is a machine. You put the thing in here that you want to get the derivative of, right? This says, take the derivative of this stuff. And while you're doing that, treat this thing as the variable. This notation is what you get after applying this thing to y, or to f of x. This is the result of applying one of these operators. This is the derivative itself. This is a command that says differentiate whatever's next to me. This is what you get out from that process. So I kind of think of it like this thing is equivalent to just the prime. Right, if you want one more like little analogy or way to think of it, as an operator, ddx of some shit is the same as that shit primed. Or you could just say ddx is equal to just the prime. Whereas dy dx is y primed, right? So kind of the prime tells you what you're gonna do. It's like, I want to prime this thing. I want to take this derivative. That's what ddx says. Dy dx says, here's what I got when I differentiated y. Here is what I got after taking this particular thing and priming it. So there, it's kind of a vocabulary thing, really. It's kind of like we're learning the language of calculus. The notation can be confusing when you're first meeting it. Be grateful we're not using Newton's notation. It was much, much worse. The dy stuff, ddx, whatever, all of this is called Leibniz notation. The prime notation is much more modern. This is what mathematicians use these days 9 times out of 10. But there is utility to the Leibniz notation. Namely, it makes the chain rule look nice, right? It also makes some other rules look nice. And there are some very important fields of mathematics where the objects dy and dx are important on their own. They're called differential forms. But you know, we're not gonna even touch that stuff. All right, I think that's all the time we have for the day. If there are any burning questions, I can take just a second here. Anything that we need to talk about before we go? All righty, then I got to scramble. We're a little bit over time, and I got another class that starts at 11. If you do want to talk more, come to my office hour today. It's a Wednesday, which means my office hour is 1 to 2 p.m. If that time doesn't work for you, you can schedule an additional office hour with me anytime you like. I have one today at 3 p.m. with another student. So don't hesitate to do that. I'm happy to do that, but please do come talk to me if you want or need help with any of these things. That's it. I'll see you guys later.